TON 618 is not dangerous because of its proximity to us. It is dangerous to the way we understand the universe. More than 10 billion light-years away, astronomers once recorded what looked like a faint blue star. But that small point of light was hiding something far more extreme. One of the largest black holes ever confirmed. Not just massive, too massive for the universe we thought we knew. Its light comes from a time before Earth existed, before the Sun existed, when the universe was still young. And yet, somehow, this object had already grown into a monster. But when astronomers first recorded it, none of that was obvious. In 1957, a routine survey at the Tonantzintla Observatory in Mexico catalogued a faint blue point of light near the constellation Canes Venatici. It looked like a star. Nobody looked twice. It was logged, assigned a number, and forgotten. Nothing about it looked interesting. Not yet. That object was TON 618. Then, in the 1960s and 70s, a new generation of instruments began probing objects like this more carefully. Spectroscopy, the technique of splitting light into its component wavelengths, revealed something that didn't belong. Hidden inside that faint blue light were emission lines, spectral fingerprints, shifted so dramatically toward the red end of the spectrum that only one explanation fit. The object was not nearby. It wasn't in our galaxy at all. TON 618 was a quasar whose light had traveled more than 10 billion years to reach Earth. The light reaching our telescopes today left its source when the universe was less than a quarter of its current age. Light that set out before our world had any history at all. A faint blue dot in a logbook, one of the most energetic objects in the observable universe. And that was only the first thing that didn't add up. To understand what TON 618 actually is, you have to understand what a quasar does. Because the black hole itself is invisible. Nothing escapes it, including light. What astronomers detect is not the black hole directly. It's the destruction happening around it. When enormous quantities of gas fall toward a black hole, they don't fall straight in. They spiral into a rotating accretion disk that compresses, heats, and accelerates. Temperatures can reach tens of millions of degrees. At those temperatures, matter radiates across the entire electromagnetic spectrum. Radio waves, visible light, X-rays, gamma rays, all erupting from a region you could fit inside our solar system. An impossible amount of energy, concentrated into one violently heated region. And all of that radiation adds up to one number, the object's total luminosity. TON 618's luminosity is estimated at approximately 140 trillion times that of the Sun. More energy than the entire Milky Way produces with hundreds of billions of stars. One object, one feeding black hole, outshining a galaxy. But the brightness was not what forced cosmologists to take this seriously. That came when researchers asked what could power something this bright. And that led to a harder question. How do you weigh something you can't even see? The key lies in the broad emission lines in the quasar's spectrum. The width of those lines reveals how fast the gas near the black hole is moving. The quasar's brightness helps astronomers estimate how far out that gas sits. Combine the two through what's called the virial relation, and astronomers can estimate the hidden mass at the center. The method carries known uncertainties. but uncertainty does not make an extreme estimate easy to dismiss. And applied to TON 618, the results pointed consistently to a number that was difficult to accept. The black hole at its center has a mass estimated at up to 66 billion solar masses. In comparison, the black hole anchoring our own galaxy, Sagittarius A star, has a mass of only roughly 4 million. TON 618 is more than 10,000 times more massive. To make that concrete, the event horizon of TON 618 would be approximately 1,300 astronomical units in radius. An astronomical unit measures the average Earth-Sun distance. Neptune orbits at 30, Pluto at roughly 40. Our entire solar system would fit inside without coming close to filling it. Astronomers now classify objects like this as ultramassive black holes, a rare class of objects that pushes black hole physics to its extremes. But the mass was not the deepest problem. The deeper problem was the timing. In the standard picture, black hole formation begins with massive stars. They collapse into black holes of a few dozen solar masses. From there, growth is gradual. Gas accumulates. Black holes occasionally merge. Mass increases slowly across billions of years. But that process has a hard limit. As a black hole feeds, infalling material heats and radiates. At a certain accretion rate, the outward radiation pressure begins to counteract the inward pull of gravity. At the extreme, the two forces, balance and accretion, shuts down. This is called the Eddington limit. It is a physical consequence of how radiation and gravity interact, and it sets a ceiling on how fast any black hole can grow. It is not a guideline. It's a limit set by nature. That is where TON 618 becomes difficult to explain. Because it appears to have reached a mass of up to 66 billion solar masses when the universe was approximately 3.4 billion years old. Run that backward through a standard accretion model, and the problem becomes clear. The number you get is nowhere near 66 billion solar masses. Not even close. The universe simply hadn't existed long enough for conventional growth to produce this. The timeline doesn't work. Something in the early universe had to have been operating outside the parameters our models assume. Researchers like Priyamvada Natarajan, a Yale astrophysicist specializing in massive black hole formation, treat this as one of the central unsolved problems in high-energy astrophysics. The question is no longer whether TON 618 exists. It does. The observational evidence is solid. The question is, what conditions in the early universe made the formation of something like TON 618 possible at all? 3 explanations are under investigation. Each one, if true, would rewrite what we think the early universe looked like. The first sounds almost elegant. Direct collapse. Some primordial gas clouds may have skipped the stellar phase entirely, collapsing straight into a black hole of tens of thousands of solar masses. No slow build-up, just an instant giant. If that happened, the timeline could work. The numbers could begin to fit. The second is super Eddington accretion. Black holes have a hard speed limit on how fast they can grow. But in chaotic environments, that limit could be exceeded. Short, intense feeding episodes that might compress millions of years of growth into a fraction of the time. The clock stops being the obstacle. The black hole simply outruns it. The third is rapid mergers. dense, early galactic environments where multiple black holes could combine on short timescales, bypassing slow gas accretion entirely. 3 mechanisms. 3 potential solutions. It seemed like the mystery had been solved. It wasn't. Because the problem is, we can't confirm a single one of them. All of these explanations require the early universe to have been more violent, more efficient, or more unusual than our models assume. That is why TON 618 matters. It is not just an extreme object. It is a stress test for our models of the early universe. And somewhere inside that ancient light, the answer may already be there. We just can't see it yet. But the mystery does not end there. One more layer is rarely discussed, and it may be the strangest part of all. The TON 618 we observe is not the same as the TON 618 that exists today. The light reaching Earth today left its source 10.4 billion years ago. That is the version our instruments record. A quasar, mid-feeding, pouring energy across the spectrum. But quasar phases don't last forever. As available gas depletes, accretion slows, the disk cools, and the quasar fades into something quieter. A dark, dormant mass detectable only through its gravitational grip on surrounding stars. What TON 618 looks like today in the actual present is unknown. We are watching ancient light from a fire that may have already died. The blazing object in our data is a fossil, light that survived 10.4 billion years of travel to tell us about a universe that no longer exists in that form. In 1957, it was a faint blue point in a logbook. Ordinary enough to misclassify, small enough to overlook. What it has revealed is a constraint, a hard observational boundary that any serious model of black hole formation must now satisfy. And none of them do. Not yet. But the deeper astronomers look, the clearer it becomes that the universe was capable of building things far stranger, far larger, and far earlier than our models expected. Whatever the early universe was doing to build something this massive, this fast, it left evidence. We are still learning to read it. TON 618 is not just a black hole. It is a question that has been traveling toward us for 10.4 billion years. We have only just begun to understand what it is asking.